Our discussions on lecture 6. So lecture 6 is about the carrier transport. Lecture 5 is about carrier statistics. So what does that mean? So lecture 5 we talk about the electron and hole density. And lecture 6 here we are going to talk about how those electron and hole move under the electric field. So that means transport. Because eventually the current is determined by two factors. One is how many electrons you have in the silicon. That is the density. And how fast the electron move. That is this transport. Current, you think about current, two factors. How many electrons you have, how fast they move. So here we are going to discuss how fast they move. And again, this is a reference chapter in the textbook. So first, we look at the mechanism called drift. So this is one mechanism to move the electron or hole in the semiconductor. This is due to the electric field. So the drift is a motion caused by electric field. And as you know, for the charged particle, either electron or hole, if you have external electric field, it will move. And the electrons will move opposite to the electric field. And holes, if positive charge, will move along the electric field. But in the material, silicon material, microscopically, the move is not straight line, right? We discussed before. It's more like a random walk with those reflections due to the scattering. But on average, over some time, then the electrons will move from one location to another location, and then this motion, on average, is called drift. Drift under electric field. And then let's look at the electron hole mobilities. So this is for the drift. And let's start from the Newton's law. So from the Newton's law, we know that if you have a mass, for example here for the hole, let's assume the mass is mp. And then the mass of the hole multiplied by the velocity of the hole, v, is mpv. So what's that? If the mass multiplied by velocity, what's that? It's momentum, right? This is momentum. Momentum. Okay. So this Newton's law tells you momentum equals to some force applied by that particle over some time. So then the force in this case will be the electric force. And the electric force by definition is charge quantity Q times the electric field. So this is like the force. And then multiplied by some time. So here we assume two scattering events. Between that, then the particle is accelerated by the electric field. For example, this particle hole is accelerated by the electric field. And then the time for the particle to travel between those two scattering events is this tau mp. That is the time between those two scattering, or the time for the acceleration. Then you will get this Newton's law. And then you move the mp to the right hand side, you will get v equals to qe tau divided by this mp. And then if you recall the lecture 2, we have something called mobility. So if you compare these two equations, you will see that V is here E is there, V is velocity, E is the electric field. So what is left is mu. Mu should be this Q times tau divided by this MP. So that's for the whole, so call it mu P. And for the electron, similarly, we get this mu N. So here the mobility is Q times the average time between two scattering events divided by the mass, effective mass for the hole or for the electron. So we have this mobility. Mu P and mu N, we have two numbers because they are different in the semiconductor. And typically, the mu P is smaller than mu N. The electron mobility is higher than hole mobility. This is generally true for semiconductors, not only in silicon, but also in other semiconductors. And the reason is the effective mass is different. So if this mu P is smaller than mu N, you can imagine that this MP is larger than Mn. So this is the effective mass. And I don't want to go too deep here. The effective mass is not the real mass. So for electrons, in the vacuum, you will have a real mass, M0, which you can measure. But in the solid, so this MP and Mn is a fraction of that effective mass, maybe 0.2 or 0.1 M0. So this is because the electrons in all holes in the solids will see some potentials, energy potentials from the nuclei. So then that will affect the effective mass of the electron or hole. It's unlike in the vacuum, you have nothing you can travel through. But in the solid, it will see some energy barrier due to the nuclei. Then it will effectively change the mass. So I don't want to go too deep into the physics there, but the conclusion here is typically the electron mobility is larger than the hole mobility. So this is very important conclusion, because later when we talk about the transistor made of the, let's say, N-type or P-type semiconductor, then we'll have the N-type MOSFET, P-type MOSFET. Then the mobility is different. That means the speed of the transistor will be different. So in the circuit design, you need to tune some parameters to compensate, let's say, to balance the N-type transistor and P-type transistor's speed, because the electron moves faster than the hole, basically. So again, this mobility is a measure of how fast the carrier can move under electric field. And the electron moves faster than the hole in the semiconductor. That's the conclusion here. Any questions? No? All right, so here, again, this velocity is proportional to the mobility times electric field. And the mobility has a unit, centimeter squared divided by volt, divided by second. This is the unit. And here this table shows some electron hole mobility for different semiconductors. And here is the silicon, and we see the number before. This is for undoped intrinsic semiconductor. Silicon is 1400 for electron and 470 for the hole. And you see that electron is larger than the hole in terms of mobility. And we do have other semiconductors like germanium, gallium arsenide, or indium arsenide. So you can see that those materials, like gallium arsenide, indium arsenide, the electron mobility is very high, like thousands or tens of thousands. doesn't work again. So here, the gallium arsenide, indium arsenide, the electron mobility is so high. So for some high-speed applications, then the industry uses the gallium arsenide or indium arsenide as the substrate to build the circuits. For example, for your like LTE wireless communication, if you have those high-frequency circuits, then you use gallium arsenide, indium arsenide to build your transceivers and so on for those high-speed application, because the electron mobility is so high, so you can switch those circuits at higher frequency. But for digital computers, we still use silicon. For your computers, the processors, it's still silicon. But we discussed that in the advanced technology nodes, like Intel or TSMC, they are not using pure silicon as a substrate. They are trying to incorporate germanium into the silicon, because as you can see that the germanium has higher hole mobility, like 1900 there. So if you have a alloy of silicon and germanium, then it can improve the hole mobility. So that's why in this advanced technology nodes, like this 14 nanometer, 10 nanometer, 7 nanometer, then the substrate is not pure silicon, it's silicon germanium. So this is the mobility. It will determine how fast the electron or hole move. That will determine the speed of your circuits, essentially. Any questions? So this is mobility. And then we talk about this scattering before. So for example, the electron, when they travel, so if you have, let's say this is a p-type doping, you have boron, and you know the nuclei of boron will be negatively charged. Because in the p-type doping, right, your boron give additional hole to the system, but then the nuclei will get negatively charged, because in total you need to get charge neutral. You give out hole, then you need to leave the negative charge behind. So if you have this center of this negative charge, then when electron move to here, then it will be repelled, because negative and negative, the electron will be reflected. So this is called scattering. Basically, you will slow down the velocity of the electron. Because the electron might try to move here, and then it will be bounce back, slow down the speed. And similarly, for if you have the n-type doping, the arsenide, let's say arsenic ion, will have positive charge to the center. Then again, if electron move here, then it will be bent like this. So no matter what, if you have doping, those dopants will act as ion scattering center, or due to this Coulomb force or Coulombic scattering. So if you have this scattering, then your velocity will be slowed down. Then the question here, if you have higher doping level, higher doping density, then the mobility will increase or decrease. Any idea? If you have more doping, then the mobility will increase or decrease for electron. If you have more of those, you will be scattered more, then you will slow down. Your mobility will decrease. So this figure shows the measured mobility as a function of doping density. And for electron, we discussed before, undoped intrinsic silicon, the electron is about 1400. The mobility is about 1400. And you can see that with the doping level here, the typical doping range, as we discussed, is 10 to the power 15 to 5 times 10 to the power 18, somewhere here. So you can see that the electron mobility decreased from this 1400 down to here like 200. This is a significant reduction of the mobility. And similar, there's a reduction in the whole mobility from like 470 down to like 150. So this is experimentally measured data for the mobility in the silicon. So you can see that there is a trade-off here, right? So then with higher doping, you are going to get more electron, but the electron will move slower. But overall, you still get higher currents. Why is that? Yeah, so you get much more electrons. Although the electron moves slower, maybe from this 1400 down to 200, you reduce by what factor? 7, right? The mobility reduced by 7x, but your density of the electron increased from 10 to the power 15 to 10 to the power 18. You increase by 1000 in terms of the density, number of electrons. Then the electron moves slower, but you have more, much more. Still, you have higher currents. So essentially, here we are looking at the current density. So for the whole current, it's Jp, Qpv, and for electron, you can imagine Jn, Qnv, and that Qnv, actually that Jn, Qnv, this equation we derived that in the lecture 2 when we talk about the metal. Because in the metal you only have electron. So again, if you look at this equation, we can think about the two factors that determine the current density. Of course, this Q, the charge quantity, is the basic constant. It will not change. So the current density in the semiconductor is essentially determined by the P or N, that is the density of your electron or hole, and the V is the velocity of the electron or hole. So to get larger currents, as we just discussed, either there are two ways to get larger current. Either you have more electron, or the electron moves faster, right? So that means either you have larger N or larger V. And you know V equals to mu E. That basically means the larger mobility. So two factors to determine the current. Because essentially you think about the current. What makes current? You have number of electrons, and then the electron move. So the current essentially determines how many electrons you have there and how fast they move. So you can imagine that equation, this current density determined by the density of the electron and the velocity of the electron, or density of a hole and the velocity of the hole. So in this example, it's about hole. And hole density P, 10 to the power 15. And then velocity here, 10 to the power 4. So you plug in the numbers. Q is the charge quantity, which is a constant, 1.6 times 10 to negative 19 coulomb. So you plug in the numbers, you will get this answer, which is 1.6 ampere per centimeter square. So this is the current density. That means in this cross section, you are going to get 1.6 ampere if this cross section area is 1 centimeter square. You are going to get 1.6 ampere. So this is how much current you can conduct in this piece of semiconductor in this case. And let's look at the drift currents. So again, this drift current is due to the electric field. You move the electron or hole under the electric field, and this current is called drift current. And then we will have this drift current will be this Q for the hole will be this QPV, and then V is velocity times V is mobility times electric field. Similarly, for the electron, you will have the same equation. The only difference is changing the P and N. So in total, you will get this because the current is a total current for the electron and hole. Those two will add up together to your total current. Electron flow and hole flow, both of them will contribute to your current. So then you can get this, you add those two together, so you get this. And then from the lecture 2, we also know that J current density equals to sigma times E. Sigma is the conductivity. So you can get the conductivity sigma equals to Qn mu n plus Qp mu p. So here, this is in semiconductor, you have both electron and hole. That's why you have those two terms. In lecture 2, when we talk about the metal, you only have the Qn mu n, because in the metal, you only have the electron. But here in the semiconductor, you can also simplify this, because with the doping, one of the carrier will be majority, the other one will be a minority. So the minority current can be ignored. If you think about the orders of magnitude, right? We talked about before. If let's say your electron is 10 to the power 17, then your hole is 10 to the power 3. So you look at those two components here, then one will dominate, right? In this case, electron will dominate. So you can ignore this whole contribution. So then sigma equals Qn mu n for the n-type semiconductor, or sigma equals to Qp mu p for the p-type semiconductor. Because this majority and minority can easily distinguish here. So, any questions? If not, then we are going to stop here.